I want to do a problem where the algebra it just comes out a little bit more complicated than this, and I just want to show you how you would do this if you have a quadratic, but not necessarily a simple quadratic. In other words, we've been dealing with things that look like x squared plus 9. We haven't dealt with anything that looks like a more general quadratic like x squared plus 4x plus 9 or something like that. So I want to show you how we would do that. Here what we have is we have the quadratic x squared minus 6x plus 11. So we do actually need to put it in the form where we're squaring something, and then we have, either it's going to be plus, a squared, or maybe minus a squared, or maybe this is reversed. But the point is, we need to square something and add or subtract a constant. So the way we're going to do that is we're going to use a procedure that you may or may not remember from algebra called completing the square. So let's do that. So x squared minus 6x plus 11. There are a lot of different ways that you can complete the square. This is taught in a number of different ways. The way that I find it easy to do is once you put it in the form so that the coefficient of x squared is 1, what you want to do is you want to take this term here and cut it in half and then simply account for it some other way. So let's just observe that I'm going to take you through my process, whether this makes any sense to you. I don't know if this is the easiest way. Let's agree that x minus 3 squared, um, x minus 3 squared minus 9 is equal to x squared minus 6x. You can verify that that's true, but the point is that what I'm doing is I'm simply cutting this b in half, putting that into its own parentheses that gets squared, and then since I now have to square the 9 and I'm going to end up with this extraneous term, I have to subtract it out again. So the point is that x squared minus 6x plus 11 is equal to x minus 3 squared minus 9 plus 11, because this is equal to that. So that's going to be equal to x minus 3 squared plus 2. So the point is that I now have an integral that looks like this. This is equal to x minus 3 squared plus 2, and since this was squared in the original, I have to square that. So now what I have is the thing that gets substituted, the thing that's going to be treated as the squared term. We've done these where the thing that's getting squared is x, but instead what I have is an x minus 3 gets squared. The factor of b, I've made it conveniently come out to 1. So the form that we're looking for here is square root of, this is going to be square root of a squared plus b squared, and I'm going to actually write u squared here because technically it's not x. I'm using some other expression where in this case u equals x minus 3. So I have actually this form, which is going to be the form x equals a over b tan theta. So the question is, what are the numbers here? Clearly we have b is equal to 1, and here what we have is we have a is equal to the square root of 2, because recall that this term here was supposed to be a squared, so that's going to be square root of 2. So I'm going to use this substitution. X equals square root of 2 tan theta. Or sorry, not x. Let me back up for a minute. It's not x, it's x minus 3. X minus 3 equals the square root of 2 tan theta. You may wonder, how can I possibly do this? And how can I just say x minus 3 equals the square root of 2 tan theta? Well, it shouldn't really bother you. It's, this is no different from saying x equals the square root of tan theta plus 3. It's just, it really doesn't matter which side of the equal sign I put the constant on. It just comes out a little nicer this way. So this gives us now the derivative of x minus 3 is equal to the derivative of this expression, which is square root of 2 secant squared theta d theta. But remember that the derivative of x minus 3 is the same as the derivative of x. In other words, this is just, you can think of it as this is dx minus d, the constant 3, where this is 0. So the point is that d of x minus 3 is just dx. I mean, I realize that I went through that algebra very fast, but you shouldn't have a problem with this because surely you must recognize that the derivative of x minus 3 is the same thing as the derivative of x, which is just 1. So they're the same. So there's no reason I can't just replace d of x minus 3 with dx. Okay, so I have here dx equals the square root of 2 secant squared theta d theta. All right, so now I'm actually ready to do the substitution. Just coming down here again, this is going to be equal to the integral of square root of 2 secant squared theta d theta over, and then down here what I've got is I have x minus 3 squared. So since x minus 3 equals root 2 tan theta, that gives me 2 tan squared theta plus 2 squared. And that, of course, equals the square root of 2 secant squared theta d theta over, this is going to be 2 squared times tan squared theta plus 1 squared. And that's going to be root 2 over 4. And let's keep going. Secant squared theta d theta over tan squared theta plus 1 is secant squared. So when I square secant squared, I'm going to get secant to the 4th theta d theta. And this is now going to equal, let's see, root 2 over 4 is actually, if I pull out a factor of root 2, that's going to be 1 over 2 root 2 times the integral of secant squared over secant to the 4th is going to be 1 over secant squared. But what we know is that the reciprocal of secant is just cosine, so this is going to be equal to 1 over 2 root 2 times the integral of cosine squared theta d theta. If you go back to the first problem that we did, or sorry, the second problem we did, I think it was, the integral of cosine squared theta is, let's see, that's going to be 1/2 theta plus 1/2 sine theta cosine theta. Okay, so we need to draw the triangle. Let's go back to here. X minus 3 equals root 2 tangent of theta. So when I draw a triangle, keep this in green for a little variety. When I draw a triangle, I can rewrite this equation as x minus 3 over root 2 equals tan theta. So that's the ratio of the opposite to the adjacent. So the opposite side is x minus 3, the adjacent side is root 2, and square root of side squared plus side squared gives us, that's going to be x minus 3 squared plus 2 on that side. And not coincidentally, you recognize that expression from there. So when we finally do the substitution, we're going to get back substitution. We get 1 over 2 root 2 times, I have 1/2 theta. So if x minus 3 over root 2 is tan theta, then that means that theta is arctan of x minus 3 over root 2. And then plus we have 1/2, let's see, cosine, we have sine theta is opposite over hypotenuse, so that's x minus 3 over the square root of x minus 3 squared plus 2 times root 2 over the square root, we have the adjacent over the hypotenuse, so that's going to be x minus 3 squared plus 2 plus 2. Okay, so that's, we need big parentheses there. Let's do a little more simplification. That's going to be 1 over 4 root 2. I'm going to pull out this factor of 1/2, and that gives us arctan of x minus 3 over root 2 plus root 2 x minus 3 over, I want you to observe what happens here. In the bottom, we have the square root of x minus 3 squared plus 2 times itself. So that's going to be just x minus 3 squared, make that a little neater, squared plus 2, but come all the way back up here. What was the whole point of that expression in the first place? That was just the completing the square version of this quadratic, so I can just replace it with the original quadratic actually, and I'm just going to do that in line, and that becomes x squared minus 6x plus 11. And of course the hardest part of the problem, the plus c.